All right, hello everyone, and thank you very much for joining us today for our media teleconference on the James Webb Space Telescope. My name is Elise Fisher. I'm with NASA's Office of Communications, and today we'll be here discussing where we are in Webb's commissioning process and what lies ahead for the next few months as the team prepares Webb for powerful instruments to begin science this summer. So as part of this discussion, we will be referring to some engineering imagery from Webb that we have shared online. So I'd encourage you to check that out at blogs.nasa.gov/web. So with us today to provide this progress update and answer your questions, we have Michael McElwain, Webb Observatory Project Scientist at NASA's Goddard Space Flight Center, Christopher Evans, Webb Project Scientist with the European Space Agency, Jean Dupuis, Space Astronomy Senior Mission Scientist at the Canadian Space Agency, Marcia Ricci, Principal Investigator for Webb's Near Infrared Camera and Regents Professor of Astronomy at the University of Arizona, and finally, Klaus Pontoppidan, Webb Project Scientist at the Space Telescope Science Institute. So each of our speakers here today will share a brief update, and then we will move into a Q&A period. When we do get to that portion of the call, you will be able to ask a question if you're on the phone lines by pressing *1. But first, to start us off, I will turn it over to Michael McElwain.
Great, thanks, Elise. My name is Michael McElwain, Webb Observatory Project Scientist at the NASA Goddard Space Flight Center. Over the past 4.5 months, Webb had a perfect launch into space aboard the Ariane 5. We completed the major deployments in the first 2 weeks, and we reached our orbit around L2 about a month into the mission. We've cooled from ambient temperatures down to our final operating temperature. And now I'm delighted to report that the telescope alignment has been completed, with performance even better than we had anticipated. There was image released back on April 28th showing exquisite image quality in each of our science instruments. These are the sharpest infrared images ever taken by a space telescope. The NIRCam instrument was used for most of the telescope alignment activities. It was the first instrument to be aligned. The released image on April 28th shows similar image quality for all 4 of the science instruments: the NIRCam, NIRSpec, MIRI, and the NIRISS and the Fine Guidance Sensor. We basically reached a perfect telescope alignment. There's no adjustment to the telescope optics that would make material improvements to our science performance. And we will regularly monitor and maintain the telescope alignment for the life of the mission. So every 2 days, we'll be doing wavefront sensing and we'll be doing corrections as needed. This is an extraordinary milestone for humanity to have successfully deployed and aligned this large infrared space telescope, which now has the capability to see the first luminous objects in the universe and observe the atmospheres of planets in orbit around other stars. This milestone was achieved through international partnerships, as you'll hear today, and demonstrating the incredible potential we have to do great things when working together. Webb is marvelous, and the team is absolutely thrilled to be at this point. So while the engineering data that we've released is beautiful, there's more characterization and calibration that we need to do before we're ready to make science observations. We've recently transitioned to the final phase of commissioning, where we moved from setting up the observatory to preparing it for science observations. We call this the science instrument commissioning phase, but in reality, it's a time where we're doing all the requisite checkouts and calibrations before we start science. I would also call this the home stretch. We've had about 1,000 activities planned for all of commissioning, and there are only about 200 activities left to complete. So over the next 2 months, we will characterize the performance of each science instrument mode well enough to know how to take science quality data with it. Complete calibrations will actually be carried out during the Cycle 1 science program alongside the selected science observations. The science instrument teams have the primary responsibility for commissioning their instruments. You'll be hearing from them today. There are 17 scientific modes that we need to bring online over the next 2 months, which requires doing a number of tests to each instrument. Later this afternoon, the Where is Webb webpage will be updated with new graphics you can use to track our progress on these 17 scientific modes. Over the next 2 months, we'll also be demonstrating the operational capabilities of Webb. such as our point and control performance, as well as the highly anticipated moving target tracking that's required for observing objects within our own solar system. And this phase also includes observatory performance characterization. Webb's architecture with the telescope exposed to space is unlike other architectures where the telescope is baffled by a tube. And this makes Webb particularly sensitive to stray light, so we'll be measuring that very carefully. We will also measure changes in the telescope alignment as we point the telescope to different locations within the field of regard. And when this phase is complete, we'll be ready to turn the science instruments loose on the universe. Next, you'll hear from my colleague, Christopher Evans from ESA. Thank you.
Hi, thanks, Mike. So yeah, I'm Chris Evans. I'm with the European Space Agency based over here at Space Telescope Science Institute in Baltimore. And at ESA, we're really excited to be part of the mission together with our colleagues here at NASA and at the CSA. ESA's contribution to the mission, in addition to the successful launch from the Ariane 5 rocket on Christmas Day, is the NIRSPEC instrument, the near-infrared spectrograph, and 50% of the mid-infrared instrument, MIRI, which has been developed through a collaboration between a European consortium and in partnership with the University of Arizona and NASA JPL. And both of these instruments are going to bring really unique, powerful capabilities to the observatory that astronomers across Europe and around the world are really eager to use once the commissioning that we're discussing today here will be finished. So just briefly on both of these, so NIRSPEC is going to give us spectroscopy of Webb's targets. That allows us to look at the physics, the chemistry, the dynamics of the targets. And until now, on space observatories, we've only been able to do this spectroscopy one source at a time, one target at a time. With NIRSPEC, we'll be able to observe 100 targets at the same time, so this will really allow us to make efficient use of Webb's precious observing time. And with NIRSPEC, we're going to use this in part to study the galaxies just a few hundreds of millions of years after the Big Bang to get a unique view of this early stage of the universe so we can learn about the formation and growth of these galaxies and their journey to the galaxies that we see today in the local universe. So alongside this, there's the mid-infrared instrument, MIRI. This extends Webb's wavelength coverage to longer wavelengths with imaging, spectroscopy, and coronagraphy. And as you've seen from the image released just ahead of this briefing, it's just going to transform our view of the local universe. The resolution and sensitivity we get from Webb combined with MIRI is just spectacular. It's going to tell us a lot about star formation, planet formation in nearby systems. As Mike mentioned, new insights into the formation and properties of exoplanets around nearby stars. And it will also give us the long wavelength information we need in studies of these distant galaxies. So pulling all this together, we're really excited at this stage of the project, going through the final commissioning stages, working with the international team, and like all the scientists and public alike involved in this, we're really excited to see the first observations in the summer, because I think astronomy is not going to be the same again once we see what this can do with these first observations. And with that, I'll hand on to Jean Dupuis from the CSA. Thank you.
Thank you. I'm Jean Dupuis from the Canadian Space Agency, based in Montreal, Canada. On behalf of the Canadian Space Agency, I really would like to thank NASA, ESA, and STCI on a wonderful job done since launch. We're absolutely thrilled to know that Webb is healthy, and we are eager to see more from this powerful space telescope. The Canadian Science and Instrument team is really pleased to see that NIRIS, the near-infrared imager and slit-lit spectrograph, is already returning high-quality calibration images. The team is very busy verifying each of NIRIS 4 observation modes and performing calibration observation. The reason we're calibrating NIRIS to make sure that it meets all of its performance requirements and that we have a good in-flight characterization of the instrument. NIRIS will then be ready to conduct scientific observation later this summer. Another Canadian element, the FGS, or Fine Guidance Sensor, is used extensively during Webb's commissioning, and it will be no doubt be critical during the science instrument commissioning as well. Webb's fine guidance systems allows it to lock on very precisely to guide star, so that the telescope remains very steady during all of its observation. In fact, the FGS greatly improves the precision of image taken by the instrument all the SI instruments, and we're very impressed with its performance so far. Looking at cycle 1, NIRISS promised to deliver incredible insights in several domains of astronomy. Astronomers around the world will use Canada's NIRISS exceptional spectroscopic capabilities to observe exoplanets. They will be able to analyze their atmosphere, looking perhaps for conditions that could harbor life. They will also use NIRISS to study and track the evolution of distant galaxies billions of light years away. We are very excited that Webb has proceeded onto this next phase. This is a long-awaited chapter for space astronomy, and we're keen to see and share Webb's first science image with the world. With that, I will turn it around to Marcia Ricky from University of Arizona. Thank you.
Thank you, John. The NIRCam team has been participating in the telescope alignment. We've issued nearly 15,000 commands to NIRCam already, all flawlessly. And the joy of participating in the telescope alignment was fantastic, seeing first light, the first fully aligned image, and so on. But we're even more excited to be moving into this phase where we're going to finish checking out NIRCam and getting it ready for science use. And to facilitate that, we've already taken more images like the ones that have been released, but using every one of NIRCam's filters so that we're ready for observers to use this suite of filters in their programs, and that they can be assured of having this fine image quality no matter what wavelength they're choosing to observe at. We're also starting to check out some of the more specialized uses of the telescope that Mike alluded to. A very important one is what we call time series observations, which is where one takes a very long series of exposures to track what's happening during an exoplanet transit. So when a planet goes between us and its parent star, and we see the little diminution of light from the parent star, and we can analyze that and learn more about the exoplanet. And we've already done the first demonstration of that, and we're analyzing the data now, and we've proven that we can upload to the facility the right commanding and the right time sequence to catch one of these transits. So that's the first step, more to come. We've also demonstrated another mode that's very important to people who want to study objects in the solar system. If they want to study, for example, ice-covered objects in the outer solar system. And this is called moving target tracking. And things in the solar system move with respect to the Earth and other things because they're orbiting the sun or orbiting their a moon orbiting their parent planet. And so we have to adjust the pointing of JWST to keep the moving objects centered in the field of view so that we get this high quality imagery. And this requires a lot of coordination between the instrument taking the data and the fine guidance sensor and the control system that points the telescope. And we've already done one demonstration of this, and again, more to come, but we are learning how to do all of these exquisitely useful, complicated methods of taking data that will fill out the whole suite of what Webb can do. And with that, I'll turn it over to Klaus Pontoppidan at Space Telescope Science Institute.
All right, thank you. My name is Klaus Pontoppidan. I'm the Webb project scientist at the Space Telescope Science Institute. I'd like to look ahead to the end of commissioning and to the release of the so-called early release observations, also called EROs. The EROs is a package of spectacular color images and other data like spectra. Their objective is to demonstrate at the end of commissioning to the world and to the public that Webb is fully operational and that it produces excellent results. It's also an opportunity to celebrate the beginning of many years of web science. There are a couple of requirements on the EROs. One is that we want to showcase all the 4 science instruments within the EROs. And we also want to highlight all the web science themes. So just to remind us about the web science themes, they cover a wide range of areas, from the early universe to galaxies over time, to the life cycle of stars, and to other worlds. That includes exoplanets. So what to expect at the very end of commissioning? Well, we'll create the ERO package at the end of commissioning after the 2 months of careful instrument commissioning. We already have prepared an expert team, scientists, visualization experts, and science communicators who will produce the ERO package. This effort is carefully planned in great detail with a couple of things in mind. One is we want to produce a high-quality product, but also one that's timely. And that means that at the end, we are currently anticipating releasing the EROs in mid-July with a more precise date to be announced later. And so with that, I'll return to Elise Fisher.
Okay, wonderful. Well, thank you very much, everyone. We'll go ahead now and begin taking questions from those who are listening on the phone lines. And we just, when you ask your question, if you could just let us know which speaker you'd like to direct that to. If you know, that would be great. So I'll go ahead and ask the operator to please start us off with Q&A.
Thank you. We will now begin the question and answer session. If you would like to ask a question, please press star 1, unmute your phone, and record your name. If you need to withdraw your question, please press 2. Again, to ask a question, please press star 1. Thank you.
All right, thank you. Then can we go ahead and take our first question?
Yes, Elizabeth, your line is open.
Hi, this is Elizabeth Howell from Space.com. I wanted to get some clarity probably from Mike, but let me know about the MIRI test image. I wanted to know a little bit more about what it's showing us beyond what's in the press releases, and also about the significance of choosing the LMC as one of your first targets for the stage of the work.
Yeah, I'll comment on the LMC, and I'd like to offer our ESA representative to speak to the MIRI image itself. So the LMC image is a really important field that's been very well characterized by other observatories like Hubble. And so we understand the stars clearly. There's a lot of very high density. We understand their positions very well, and so we can use them for astrometric calibrations, of course, you know, of the science instrument focal planes relative to each other. So that's important for our calibration of the observatory, of the telescope relative to the science instruments. Of course, these images are also very spectacular. And so, yeah, in the near spec, you can see a pattern which represents the microshutter array covering up some of the field there. So it's actually blocking part of the field. And something else that you may not have noticed, but you see the star density in the fine guidance sensor actually looks higher than at the other field points, and I think that's really interesting. The FGS actually has a very large bandpass and also a little bit wider detector pixels, and so it actually has really high sensitivity, and you can see that in this image. So I'd like to offer the MIRI image discussion over to Christopher Evans.
Thanks, Mike. So it's Chris Evans from ESA. So just to add on the LMC in particular, so this is a really nice science example of what Webb will do for us in the coming years. So we've done a lot of studies of star and planet formation in our own galaxy, but here we're looking at in the Magellanic Clouds, so small external galaxies where they're chemically less evolved than our own Milky Way. So this gives us a chance to look at the processes of star and planet formation, the formation of disks around stars, in a very different environment to our own galaxy. And Spitzer did amazing things for doing kind of wide surveys in the Magellanic Clouds. But as you can see from the comparison today, ultimately we were limited by its spatial resolution. And now you can see how all of those large sources are resolved into multiple components. You can see the gas traced out by MIRI. So this is going to give us just an amazing view of the processes in a different galaxy for the first time, cutting through the dust because we're using the mid-infrared to look through the material that otherwise would be obscured at visible wavelengths.
Great, thank you both. So operator, we can take our next question here.
Bill Harwood, your line is open.
Thank you. It's Bill Harwood, CBS News. And I'm not sure who to direct it to, maybe Michael or Marcia, but can you talk a little bit more about what instrument commissioning actually entails? I mean, obviously, everybody's checked their instruments out to this point, but I assume now it's imaging and taking spectra with the optics, you know, perfectly aligned. I mean, maybe just a little bit more detail about those 17 modes you're talking about to give us some sense of what commissioning actually means now that you've got this thing lined up. Thanks.
Marcia here, I'll take a crack at that because we're in the thick of it right now. So, for example, we have some pieces called grisms, which can be put into the beam, and that when we put one of those into NIRCam's optical train, when we rotate the pupil wheel to that position, instead of seeing a field full of stars, we see a field full of each star turned into a spectrum. And those spectra aren't particularly useful unless we know exactly what wavelengths we're observing. So, for example, we have to do a wavelength calibration all across the field of view when we put this piece of optics into the beam. And likewise, when we just do regular imaging, everyone's going to want to know, okay, we see these stars, but in terms of physical units like watts, how bright are those objects? And so we have to go through a process to actually figure out how to convert the units, engineering units that we get into actual things like watts. And so that's a lot of what we're doing right now is going and getting things into the final form that astronomers will want to use.
Thanks.
Yeah, I could just say a few words about, there's also a follow-on question about the science modes, the 17 science modes. So as I mentioned in my opening speech, there will be an update to the Where is Webb webpage where they'll be listed later this afternoon, I believe, is when that'll be updated. So each of the 4 science instruments has 4 or 5 of these science modes that will be characterized. So I think you mentioned, you know, imaging, spectroscopy. For example, NIRCam, it's imaging, wide field slitless spectroscopy, coronography, and time series observations with imaging and using the grism that Marcia was just talking about. So these are the types of modes. Each of those modes has different criteria that we're looking for, that we want to see the performances being met. And that gives us confidence that we're able to do the observations for cycle 1 and get very high quality science data products from them. So each one of these modes will be reviewed independently. We'll have a board that will do the review. The science instrument team will present their data. And then once that's approved, then the observatory can actually schedule cycle 1 science observations or carry out the EROs, the early release observations that Klaus briefed.
Thank you both. Let's go ahead and take our next question.
Marcia Dunn, your line is open.
Yes, hi. 2 questions, please. Dr. McElwain, you mentioned that you're of 1,000 milestones, you've only got 200 left to go. You're in the home stretch. I mean, obviously the worst is behind you, but is it pretty much home free at this point that you can finally breathe a breath of relief and know that there's no ghosts out there, no gremlins that are waiting for you at this point, that you've pretty much got an instrument that you wanted to have all along? And also, what if I could have some reaction to the images, the MIRI images that were released today with the before and after with Spitzer and Webb? I mean, the clarity difference is astounding, but what were your reactions, and how much better is this from a scientific point of view if you're studying these galaxies? Thank you.
Sure. So I'll answer the first question. So we've gotten through a very large part of commissioning. The alignment of the telescope required that all of the systems were functioning and working properly. And so we're able to communicate with the observatory, get data, and process it on the ground. And so overall, the observatory performance has been phenomenal. And so, yeah, as I mentioned, we're really in the home stretch. At this point, we're characterizing and calibrating both the observatory and the science instruments. And, from my perspective, there's always risks going forward, but I have great confidence that we'll get to the finish line here and we'll have a terrific science mission and with tremendous scientific discovery in the next few months. So I'm just super excited to be at this point. I'd like to, I guess defer, go ahead, Marcia. Yeah, I wanted to defer to some other colleagues that might want to respond about the images.
Yeah, I will comment on the comparison with Spitzer because I also worked on Spitzer. And, from a sort of an intellectual standpoint, you can appreciate that the images from Webb are going to be better because we have 18 segments, every one of which is larger than the single segment, so to speak, that formed the Spitzer telescope's mirror. But it's not until you actually see the kind of image that it delivers that you really internalize and go, wow, just think of what we're going to learn. Spitzer taught us a lot, but this is like a whole new world, just unbelievably beautiful.
So Chris Evans again from ESA. Just to add to Marcia's comment, so we've been doing a lot of work in the Magellanic Clouds over the past decades, and we've been doing studies with Hubble with its fantastic resolution in the visible, but suddenly being able to see this resolution at the longer wavelengths is just fantastic. Until now, we've been limited by the angular resolution with the Spitzer performance. Suddenly, you can resolve those into individual stars. You can see all the structures in that image. It's just going to transform our view of local galaxies like the Magellanic Clouds. That will allow us to study the properties of stars in these different environments that are more similar to the galaxies in the early universe, so we can really learn about some of the processes that went on at very high redshift, complementing the work that NIRCam, NIRSpec, and MIRI will be doing in those early systems.
All right, thank you all. We can take our next question here.
Irene Klotz, your line is open.
Thank you. Irene Klotz with Aviation Week. I have two questions, please. The first for Mike. Are you able to characterize technically the better than expected performance and also maybe with a metaphor or an analogy of what you expected and what you're seeing? And probably for Klaus, I believe there was one Russian PI and a few co-PIs in Cycle 1 for science. Is any of that, if that's correct, is any of that being affected by any of these sanctions stemming from the issue in Ukraine? Thanks.
So, Mike, would you want to jump in on that first question? Oh, thanks, Mike.
Yeah. So the first question about better than expected. So basically, our telescope alignment sets our static wavefront error, and that tells us how well the observatory is able to perform. And our static errors are actually significantly better than what we had budgeted from an engineering standpoint, from systems engineering. And really what that means is that we put the mirrors into position with better accuracy and precision than what we had budgeted for. And so we're actually doing much better than requirements. The impact there is that we have better sensitivity. So we have some better encircled energy. That's a metric that the scientists use. And we would also have potentially better resolution at shorter wavelengths than we had planned for with Webb. And so this is, really exciting that we're in that position. I'll give the caveat that there's, so we have this alignment, but then there's also an important component, that's stability of the alignment that I'd mentioned as well. And that's a test that we're actually planning to start tomorrow. There's a blog post about that posted last week. And so that'll give us a sense for how stable the alignment is. And so that's also an important component. But the fact that we have a static alignment that's so tremendous, we have confidence we can always put the alignment back into place, even if it is to drift. And so that gives me really great confidence that we'll have, the ability to do tremendous science. And I don't know if I haven't thought through a metaphor or an analogy, so apologies, I don't have that at this time.
But I'll comment that when NIRCam measured the shape of the stars through our various filters, we found that the telescope is actually what we call diffraction limited, that is operating at the physical limit at a wavelength half of what the requirement was. And that's just, amazing that the image quality is that excellent, and that's going to help our science quite a bit.
All right, so this is Klaus von Tobben at Space Telescope. I can address the other question regarding investigators based in Russia. So I can note that at Space Telescope, we have not received any direction at this time regarding investigators on science programs from Russia, so it has not had an effect one way or the other.
And Irene, this is Elise with NASA. I can follow up with you if you have additional questions there too after the call. So we can take our next question.
Jeff Faust, your line is open.
Hi, good morning. Jeff Faust of Space News. Question for Klaus. I wondered if you could identify any of the objects that you're going to use for the early release observations, or at least considering as candidates for the early release observations. And then also, assuming everything sticks to the current timeline, when would the Cycle 1 observations formally begin? Thanks.
All right. This is Klaus von Tobben again. I'm afraid I can't reveal any of the ERO targets that we will observe. There's a couple of reasons for that. One is we'd really like it to be a surprise, but also we haven't taken those data yet, and they are to some degree dependent on exactly when we can schedule them. And we'll schedule them after the instrument teams have declared the instruments and modes ready to observe the EROs. So we prefer not to put ourselves in a box. But we certainly hope that you all will join us in celebrating when they do come out. Let's see, what was the other question? When does Cycle 1 start? Oh yeah. So this Cycle 1 will begin formally after the release of the early release observations. It is possible that there is some time before that where we'll be obtaining some science observations. But even if we do, those data will not be released until the ERO press briefing.
Thank you. Let's take our next question.
Sandra Wicks, your line is open.
Hi, this is Alex Witzy with Nature. Thanks for taking my question. It's also for Klaus on the ERO. I know you can't talk about the targets specifically, but can you talk a little bit about the process through which those targets are chosen? Like, is there a committee particularly tasked with coming up with what these targets might be? How does that work? What are those conversations like? Who are the folks who are on that committee?
Yeah, so Klaus von Tobben again. So yes, there was a committee set up that included representation from all our partners and from NASA who looked through a large number of potential targets. And they created a ranked list. So this was a long list because, again, the exact targets are determined to some degree, or in some cases to a large degree, on when we'll be able to observe them. And so we're basing the observations out of the recommendations provided by that committee.
And who makes that call?
So the committee provided that ranked list that's prioritized. So we go from the top of that list. Right? We pick the top one that is observable at the time that the EROs will be released. And apart from that, a lot of work has been going into then defining the observations based on those targets.
Thanks.
Thank you. Let's go to our next question.
Lucy, your line is open.
For AFT, so again for Klaus, again about the early release observations, can you expand a little bit on the difference between the images that we've seen so far and the ones that you'll be releasing mid-June? What can we expect, and maybe can we talk, is it correct to talk about the first scientific images for the EROs? Thank you.
Yeah, Klaus Montalban again. A key difference between the images you've seen so far and the EROs, well, I guess there are two differences I want to highlight. One is that the images you've seen so far were taken for calibration purposes and commissioning purposes, right? So they're images of star fields, because star fields are useful to measuring the geometry of the instruments. We have lots of stars. They're useful for calibrating the instruments. But they're not observations of astrophysical targets that you may be familiar with from Hubble, right? There's a galaxy or some other object. So the EROs will be images of actual objects that are picked for their ability to demonstrate that the observatory can do science. The other difference is that the EROs will be the first time we release color images. So again, color images is a way that, in a way that you're used to seeing from Hubble. Of course, these are infrared colors, not colors in the visible spectrum, but they're still colors nonetheless. Right? These are real colors, and what we do when we create color images from these is essentially we are translating the infrared colors into visible colors that humans can see.
And just to add to that as well, Chris Evans, so it will also include a release of some of the first spectra from the observatory so that we can demonstrate the other modes that the instruments will have, so it can show the range of techniques that astronomers will have once we go into regular operations.
Great. Thank you both. We have time here for one or two more questions, so let's go ahead and take the next one.
Ken, your line is open.
Hi, this is Ken Kramer, Space Up Close. Thank you for taking this question and for doing this. My question is for Marcia. Can you talk about a little more detail about the time series observations and the moving target tracking, the work you did to accomplish this, and also want to know, to observe these exoplanet transits, how long do you have to aim it, as well as the moving target in our solar system, how long do you have to aim that? Thank you.
Okay, for the time series observations, we want to start enough ahead of the actual transit that any disturbances in it with the detectors or anything in the instrument have all settled down, because the time series observations involve measuring very, very tiny changes in signal. So everything needs to be as stable as possible. And we estimate that we want to start taking the data about 30 minutes ahead of when we would actually call the science observation beginning. And depending on the type of star and the type of transit, people have various rules of thumb of how much time they want ahead of time, but Hubble and ground-based experience suggests that a good baseline before the actual transit is something like a couple of hours, and that'll vary a little bit from one observation to the next. So one has to get to the target and start taking data, let everything settle, and then you can start acquiring the data that you're actually going to count on. And of course, once you get to the target, you don't disturb anything. You leave the filter setting, everything as it was. For the moving target tracking, the thing that matters here is that because the objects are moving, we have to know exactly how they're moving through the solar system. And so we have to have an accurate what's called an ephemeris, a tabulation of where that object is going to be at which time, and that has to be uploaded as part of the command structure so that all of these handshakes of pointing and synchronizing observations get done correctly. And the Jet Propulsion Laboratory, among other places, keeps very accurate ephemerides for all the objects that have been tracked in the solar system. So when someone wants to observe, let's say, an asteroid or one of these distant Kuiper Belt objects, they have to make certain that they have the ephemeris for the dates that their observation is planned for, and then that information has to get folded into the command upload, and then one does not need to get to the target particularly ahead of time, but I think there is a few minutes of getting everything synchronized to get that to work.
And how long does it stay on the target?
That depends on what one is observing. If you're taking a spectrum, you may need to stay there longer than if you're just taking an image. The tracks can go for a couple of hours if that's necessary.
Thank you.
This is Jean Dupuis from CSA. I'd just like to add that during moving target observation, also we must, I guess, keep observing the guide star. And I think we've done a first test, I think, last week, and it worked really well. So this is very encouraging.
Thank you all. Let's take our next question.
Bill Harwood, your line is open.
Yeah, thanks again, Bill Harwood, CBS. I wanted to go back to Klaus talking about the nature of infrared pictures. You know, I think the public is so used to Hubble and the visible light imagery. I'm just wondering, even though you're putting colors with some interpretation into an infrared image, is it sort of like some of the pictures we've seen from Spitzer, where you see some greens and blues and a lot of reds? I mean, I'm trying to get a sense of what the public might think of these images when they're so used to things from Hubble, if that makes any sense. Thanks.
Yeah. So this is Klaus Pontoppidan. I think you're alluding to when you look at a Spitzer image, you may get this impression of you're looking at primary colors like red, green. And a reason for that is that Spitzer did not have many filters, and they were very much separated in wavelength. And Hubble had many different filters, many more. So and they were closer spaced together, and that allows you to mix different filters such that you get a broader range, a broader color gamut. So in this sense, Webb is much closer to Hubble. We have many filters to choose from. We can choose filters that are closer together. And so already initial tests indicate that the images that we will see in the EROs in terms of color quality and aesthetic quality will be more similar to what you're used to from Hubble and from Spitzer.
Thanks.
Thank you. And now we'll take the last question we have time for today.
Marcia Smith, your line is open.
Thanks so much. I was wondering, Mike, if you could just very briefly again explain why you have to check the alignment every 2 days, and why is it every 2 days instead of every 3 days? And do the astronomers need to pause their observations while you're doing any of this, whether it's when you're checking the alignment or if you have to make changes? Does that affect their observations? And also, does the cycle 1 observations, do they begin in July?
Great, thanks, Marcia. This is Mike McElwain. Yeah, so the baseline plan is to check the alignment about every 2 days. It's not exactly every 2 days. So once we get into science observations, and actually we've just recently transitioned where we're now uploading long, 24-hour observing plans that the observatory just executes and works through all the various observations. And so these will be scheduled alongside other science observations when they fit in. The exact cadence is not really critical. The original requirement for the mission was that we do corrections no more frequently than every 14 days, so 2 weeks. And so we wanted to get multiple sensing measurements before we get to that time period, and that way we could understand. The thing that we're correcting for is actually structural changes of the telescope. We expect those to be quite small, but over time, over the life of the mission, we anticipate, more than a 20-year mission at this point. We have propellant for more than 20 years. The backplane, for example, will continue to settle, and there might be mechanical creep in the backplane, and so we would want to take out those, we would want to correct those sort of systematic drifts of the telescope. We also anticipate, as I was mentioning, thermally there's going to be thermal distortion when we're pointing to different points within the field of regard, and we do not really plan to correct for those thermal distortions, but just the systematic large-scale drifts of the telescope. We will also make available PSF library, PSF qualities to the observers, and so we get those 2-day measurements, and we'll understand what the PSF within the instruments across the field should be. So that's something that we can use for science as well. So that's another benefit of taking regular measurements. Of course, if there were some event, we would be aware that something were happening, and we could correct as needed. And I think the other question you asked was about cycle 1. And so I think Klaus might have touched on this, but as soon as the science modes are enabled, we can start taking the cycle 1 data. The mode enabling means that we're ready to take the science data. And so we could start taking the data. That data won't be made public until the EROs are released. And so, we'll just see, our priority is to get through the instrument characterization and checkout so we don't delay the EROs. But if we have time in the schedule, we would certainly fill them with science observations. Thank you.
Great, thanks, Mike. And so as mentioned, that's all the time that we have for today. But again, if you have further questions, please feel free to reach out, and our media team will be happy to help. So thank you very much to all of our speakers, those who dialed in on the phones, and please continue to stay tuned for updates at blogs.nasa.gov/web, and also to follow along with our Where is Webb tracker online. That's at web.nasa.gov. Thanks very much.
That concludes today's call. You may disconnect at this time. Host, please stand by for your post-conference.